Here is an introduction to low-mass stellar evolution to accompany Chapter 22 of the textbook Astronomy from OpenStax. So we've talked about how stars are powered for most of their lifetime. There's hydrogen burning in the core, and eventually all of that hydrogen is going to be consumed, right? It just can't last forever. How long a star is burning hydrogen in the core, which defines its presence on the so-called main sequence of the HR diagram, as we learned earlier. That's going to depend on how much fuel you have to burn, which is, of course, related to the mass of the star, and the rate at which the fuel is being burned, which is naturally going to be related to the luminosity because it's the nuclear reactions, burning that fuel that's generating the light ultimately that shines from the star. In the introduction to the HR diagram lecture, we saw that just empirically, you can sort of show this analytically, but empirically we see that the luminosity goes as the mass to the fourth of the star when it's on the main sequence. The amount of time it's going to take to consume your fuel is, of course, going to be related to the amount of fuel divided by the rate at which you're consuming that fuel. Right, so just your mass divided by your luminosity, if you pick the right units, that's going to be just equal to a time. And so then, if our luminosity is proportional to the mass to the fourth, we can plug that in, and we see that the time on the main sequence would roughly go as mass to the -3. You can then calibrate this to the main sequence lifetime of the sun. We understand the sun very well, and we know that its lifetime is going to be about 10 billion years. Empirically, you can check this and get a slightly more precise exponent there. So if you take the lifetime of your various stars here, so these are the different spectral types, and you plot that versus the mass. So here I actually have the log of the main sequence lifetime versus the log of the mass, and you can fit that with a line, and then in this log-log space, the slope is -2.6, the intercept is 10, exactly as we'd expect. And so then what this means is that your lifetime on the main sequence is 10 billion years times the mass of the star at the beginning of its lifetime, divided by a solar mass to the -2.6. And that's how you can calculate what the main sequence lifetime is. So just as an example, we'll pick an O5 star. So this is a very massive star. The so-called zero-age main sequence mass is 40 solar masses. We can plug the numbers into here. We take our 10 billion years times this ratio of our mass of the star to a solar mass. So that's just 40 to the -2.6. And you do some rounding, and you can see that this is about a million years, 0.7 mega years to consume all the hydrogen in the core. So, that's roughly how long it takes, and for any given initial solar mass, you could calculate what that rough lifetime would be given this equation here. So ultimately, you run out of the core hydrogen fuel, and your core is now made of helium, right? Because the hydrogen has been burnt into helium. It's not hot enough to fuse that yet to undergo nuclear reactions. So instead, your core is just going to contract because there's not any pressure generated from the nuclear reactions, from the heat at the core, to counteract gravity. So gravity is going to win, the core is going to contract. And it's going to heat up because you're compressing material. Eventually, it's going to become hot enough that the hydrogen shell that's around our helium core, it can burn. Okay, so that's going to release a lot of energy. That's going to then give more light to power the star, and it's going to add helium to the core because you have a hydrogen shell around the helium core. So helium is basically going to kind of fall onto the core, if you want to think about it that way. The hydrogen shell requires high temperatures to burn, so these are higher than the temperature you need in the core because the density is lower. And so the stellar luminosity increases, right, relative to what it was previously. So when you lose the core hydrogen burning, when that ends and you're now doing shell hydrogen burning, the luminosity of the star is going to go up. Because the luminosity is going up, this is sort of a hand-wavy explanation, then the outer layers are going to puff up. So really, if the core contracts, the envelope must expand. So the stellar radius is going to increase. Because the radius is larger, you'll recall from our introduction to the HR diagram lecture that means that the black body temperature is actually going to be lower, and so the star is going to become redder. And so this is how you make a so-called red giant star. So if you look back at our HR diagram with all of the sort of nearby stars around us, you have your main sequence, and then there's this branch here, and these are the so-called red giants. They're redder because their radii are larger, so they have a lower black body temperature. They have larger radii, so they're located up, to the upper right in this diagram, and that's how you get a red giant, is from this shell hydrogen burning process. Now, because the luminosity is higher for this shell hydrogen burning than for the core hydrogen burning, and because you just have less fuel, the time spent on this red giant branch is a lot less. So something like, a few percent, even 0.1%, up to 10% of the main sequence lifetime. So stars spend, 90% or more of their lifetime on the main sequence, and somewhere between 0.1% and 10% on the red giant branch. Now, eventually, you're adding helium to this core, and also the core is continually contracting. The envelope's continually expanding. This thing's getting larger and larger. Eventually, your core has contracted enough that it's hot enough that helium can ignite. This is at like 100 million degrees or so. So a little less than 10 times the core temperature of our sun. Because the core is no longer contracting, the envelope is no longer puffed up. So these two things kind of act as like a mirror. If your core contracts, your envelope expands. If the core isn't contracting, the envelope isn't expanded. So the radius then decreases. The black body temperature is actually raised a little bit. I have it as lowered, but that's not true. It's raised. So the star is going to become a little bit bluer. Your core helium burning is going to start at roughly the same core temperature for all stars, right? There's just a nuclear reaction that can turn on at a certain point. And so you're going to have roughly the same helium core mass and helium core temperature, which means that the luminosity for any given star when core helium burning can happen is going to be roughly the same. So regardless of what my initial mass is of my star, by the time I've evolved to have core helium burning, my luminosity is about the same. Your actual radius that you have and your black body temperature is mostly going to depend on just how large the remaining hydrogen envelope is. And so that means you're going to have a spread in black body temperatures. Your star may be a little bit larger in radius or a little bit less, just depending on how big that envelope is, and that radius, as you know, for a fixed luminosity, directly gives you the surface temperature and therefore the color. So you're going to have a spread in colors or a spread in effective temperatures, and that leads to the so-called horizontal branch. So this is for an actual grouping of stars here. You can see there's still some main sequence stars left. You have your red giant branch stars, and then there are several on this thing here called the horizontal branch. And now we know it's horizontal because these are all roughly the same luminosity, because they have all roughly the same amount of helium in their core. And there's a spread because you started out with more or less hydrogen to begin with in these stars. The lifetime here is much shorter than the lifetime on the main sequence, and that's because you have helium burning. So initially anyways, the helium burning is going to be through the so-called triple alpha reaction. A helium nucleus is called an alpha particle. I combined 3 of these to make carbon, so that's triple alpha. And so that's converting helium to carbon in the core. If you look at the energy generation rate versus the temperature, you'll see compared to our hydrogen burning processes, the triple alpha is extremely steep, much steeper temperature dependence. And so then that means that as time goes on and the temperature is increasing, you're going to burn more and more helium more and more rapidly. It's going to be a very short horizontal branch lifetime. Depending on your initial mass, you're talking about, a mega-year up to hundreds of mega-year. It's still, much shorter than the lifetimes we're looking at for the main sequence that, are in billions of years is more typical. Okay, so, eventually your core helium burning is going to run out, and this next stage, this is a lot like a red giant branch. So that's why I'm just flashing it here, and the stuff that's different is in red. So before, the core hydrogen ran out, you have shell hydrogen burning, and your core contracts, therefore the envelope expands, and you move up in luminosity and redder in the HR diagram. Well, the same thing is going to happen when the core helium burning runs out. Your core is mostly carbon and oxygen. The oxygen is caused by helium being combined with carbon. So that's the other helium burning process. So you have mostly core carbon and oxygen left. Your carbon and oxygen core is going to get larger due to the helium shell burning. Your helium shell is quite hot. The luminosity is going to increase, so the star is going to move up on the HR diagram. Same argument goes for the star expanding and becoming redder. And so now we have an asymptotic giant branch star. So these stars evolve to an asymptote that is defined by the red giant branch, and so they're asymptotic giant branch stars, and they're indicated here by the blue squares in this diagram. So these are known AGB stars, and you can see them where they really are on the HR diagram. And here, similar argument goes: high luminosity, less fuel. You're not on the AGB phase for very long. You're talking a few mega years, typically. I focused on the shell helium burning. You also still have hydrogen, so there's shell hydrogen burning as well. So what these AGB stars look like is you have a carbon-oxygen core. You then have a helium burning shell surrounding that carbon-oxygen core. You have an inert helium layer, so helium that you can't quite burn. Then you have a hydrogen burning shell that's adding to the helium shell mass here. And then a hydrogen envelope, so no reactions going on there. We can piece this all together. Let's watch this movie. Star contracts, has core hydrogen burning. It's on the main sequence. That runs out. It now does shell hydrogen burning. That's the red giant branch. That already finishes. It's now doing shell helium and hydrogen burning, becomes very large as an asymptotic giant branch star. Does some funny stuff here. There's things called thermal pulsing, whatnot. Eventually, all the shell fuel runs out, and this star is then going to expel its envelope and cool off and form this hot thing called a white dwarf that we'll talk about more in a moment. And you can watch that movie a little bit slower at our own pace. We have our main sequence star. We're burning hydrogen in the core. This is going to be billions of years roughly. You then have your shell hydrogen burning. You climb up the red giant branch. Core helium can ignite. You spend time on the horizontal branch. You run out of core helium fuel. You do shell helium and hydrogen burning, move up the asymptotic giant branch. Eventually, the core contracts enough that this thing's very hot, and you can expel the envelope, and you become this dim object called a white dwarf. Okay, so besides being cool, we know how these stars evolve. These stars are also very important for nucleosynthesis. So by that I mean the formation of the chemical elements in the universe. So we've talked about how the helium, carbon, and oxygen are produced in these stars through the sort of more normal burning phases. You can make, and do make, heavier elements in the asymptotic giant branch phase. So what happens is when you have this hydrogen burning shell and this helium burning shell, these two can mix. How this all happens, can be a little bit complicated. So the point here is these things can mix together. What ultimately happens is you create a lot of carbon-13 that reacts with helium nuclei to do carbon-13 alpha N and produces a lot of neutrons. You can also make some neon, specifically neon-22, and that'll also react with helium to make neutrons. The point is that these helium and hydrogen burning shells wind up creating a lot of neutrons. So the neutrons, what happens is they can be captured by elements that are left behind from a previous generation of stellar evolution. So a star, typically in the universe, it's forming out of some gas cloud that's laying around, and that very well may have been, and often is, enriched from a previous generation of stellar evolution. So you have elements that are made from those earlier generations, for instance, from a high mass star that we'll talk about next time. So these elements that are in the star already are basically being bathed in a neutron bath in this region, near this helium and hydrogen burning shell. So you have all these neutrons hanging out. They'll be captured by these heavy elements, and a given nucleus will capture a neutron roughly once every decade. Right? So that's not that fast. That's a relatively slow process. So we call that the slow neutron capture process, or the S process. And it turns out this makes, about half, or at least a very large fraction, of the chemical elements that are heavier than iron. So what's shown in this picture here is your friend, the periodic table, and the different coloring scheme for these elements tells you roughly the amount of material that was made by these different sites in the universe. Here we're focusing on dying low mass stars. These are these AGB stars that we're talking about. And you can see a lot of the elements in green here. These were ones that were made in a significant amount by these low mass stars. So that's pretty cool. Anytime you encounter any of these elements, that you see around, they were made in a low mass star during its death. So how these elements actually make it out into the universe is because the envelope of these giant stars are expelled. So in the red giant branch phase, you can have tens of % expelled, and that's really simply because, if you're very far away from the core of the star, gravity is going to be very weak, and so it's easy for the envelope to escape. Now, where you have a ton of mass loss and you expel most of the envelope of the star is after core fusion completely ceases. So when you're in this asymptotic giant branch phase, your core is continually contracting the entire time, and it's getting hotter and hotter and hotter. And at a certain point, the radiation pressure just becomes so large that you have this hot thing left behind called a white dwarf that we'll talk more about in a couple lectures. This hot thing is it's expelling so many photons that these basically blow off the envelope of the star. And it produces this thing that you see here, this beautiful object called a planetary nebula. The name doesn't have anything to do with planets. It's a misnomer based on old misconception, but astronomers are stubborn and they don't want to rename things. So you have these beautiful objects called planetary nebulae, and these are the remnants of low mass stars. And so this is how elements are then blown off into the universe. You had your envelope of your star where, for instance, your S process nucleosynthesis occurred, and this stuff is blown off into the universe to be incorporated into future star formation. And these objects, this is a very short phase of a star's lifetime, or really of its death, I guess. You can only see these for about 50,000 years. Because you got to be close enough, to the hot remnant for this stuff to all be visible. And that is it for this introduction to low mass stellar evolution for Astronomy 1000.